purpose of this experiment is to examine the effect boiling an egg at different times has on the chemical structure of the egg. We'll be following the procedure shown and discuss the various chemical processes at play throughout this experiment. First, water must be added to a clean pot. The water level should be above the height of the eggs. Take this pot and place it on the stove. Turn on medium heat to the pot so we can get a rolling boil. Before we get into cooking our eggs, let's talk about an unboiled egg. An unboiled egg has its protein in a native state. The amino acids are folded in a very specific way that gives the protein its shape, and that shape gives the protein its properties. When we begin to boil the eggs, denaturation occurs. Denaturation is what happens when heat is applied to the eggs. Chemically, this process by which the chains of amino acids are changed from the original or native state, the heat coming from your stove denatures these proteins by disrupting some of the bonds that hold the molecule into shape. In the case of hard-boiling eggs, the proteins clump together and solidify, causing the egg white and the yolk to harden. As the egg cooks, heat energy will be transferred through the shell into the interior of the egg. This means that the boiling of an egg is an endothermic reaction. Once the water has reached a rolling boil, carefully add 3 eggs to the pot. Take extra care not to crack them. If the shell cracks, the egg will heat up too quickly and ruin our observation section of this experiment. We want to make sure to compare the eggs at different stages, so they must all be intact and cooked at different times. Set a timer for 8 minutes. We will be removing an egg at 4 minutes, 8 minutes, and 15 minutes respectively. While your eggs are cooking, set up your observation station. Get a hold of your extracting tool, a ladle, and set out egg cups to hold the eggs once they were removed from the water. Once you hit your first time mark, remove the egg with the ladle and run it under cool water to halt the reaction from proceeding any further. Since it's the proteins that cause the egg white to solidify when you cook it, and then the yolk, egg white proteins are long chains of amino acids as discussed. In the raw egg, these proteins are curled and folded to form a compact ball. Weak bonds between amino acids hold the proteins in the shape until we start heating up the eggs. As they're heated, the weak bonds break and the protein unfolds. Then its amino acids form weak bonds with the amino acids of other proteins, a process called coagulation. The longer you cook an egg, the more and more protein bonds form. A soft-boiled egg does not have that many bonds formed. Now, let's take a look at our soft-boiled egg. We'll crack off the top to observe the structure of the egg whites and the yolk. We know that egg cooking is an endothermic reaction, so the egg whites solidify first. As we can see here, a little bit of the egg white is solidified, but not very much, and the yolk is definitely liquid. We know that as we heat the egg continually, weak bonds break and protein unfolds, while the amino acids form weak bonds with other proteins. Obviously, in a soft-boiled egg, not many of these bonds are reforming. Now, we're going to start looking at a hard-boiled egg. While a hard-boiled egg is hot, it should still have a bit of a wobbly, gel-like flexible solid, which is because the bonds between proteins are still being formed. Once it completely cools, the protein bonds will be permanently set, like a solid. I must say, the last egg is the most exciting chemical reaction we can talk about, but here we're going to observe a hard-boiled egg, and you can think back to what we observed in the soft-boiled egg. We can definitely see that the yolk has a much more solid-like structure after being applied to longer amounts of heat. This is because more bonds between the proteins have formed as a result of the endothermic reaction. As we finish taking a look at the hard-boiled egg, we're then going to dive into the incredibly interesting chemical process that happens when you overcook a hard-boiled egg. Apart from the folding processes, there's some chemical reactions that can occur in egg proteins when they're subjected to heat, especially excessive heat. This can also be seen in older eggs, but at elevated temperatures is when this is most commonly seen. These reactions observed involve cysteine side chains, and the simplest is a replacement of SH by an OH group, transforming the cysteine into a serine molecule. A byproduct of this chemical transformation is hydrogen sulfide. This gas is associated with that rotten egg smell that we all know. Hydrogen sulfide gas is toxic, but in the case of an egg like this, it's in such small quantities that it can't pose a health risk to someone eating it. Seen in this reaction, it involves the amino acid serine. The protein phosphatidyl found in egg yolk is really rich in serine, and most of the associated hydroxyl groups are normally esterified with phosphoric acid. Phosphatidyl is able to complex essentially all of the iron present in an egg. This is what is seen around the outside of the egg here, that greenish tint. The prolonged cooking causes the cleavage or saponification of serine's phosphoric esters, leading to free phosphate. This means that that complex iron in the yolk is suddenly released, and it can be seen at the egg yolk to egg white interface in between. Iron cations soon encounter hydrogen sulfide, which is released by the transformation of cysteine serine in the egg white. This results in the formation of the insoluble brownish-green iron sulfide. That is exactly what you see here, as that dark ring that can be observed in hard-boiled eggs that have been cooked especially a long time. Now that we have learned that the impact heat has on cooking eggs and how this works to disrupt and reform bonds to make it hard or soft, let's look at all three eggs next to each other. After making our final observations, we then want to throw away all of our materials used into the appropriate waste containers. In this case, nothing is especially dangerous, so we can just throw everything in the trash. Once your workstation is cleared of the compounds, we can then clean all of our glassware very well so it is ready for the next chemist to use. Please make sure you effectively scrub all of the substrate off of the glassware, because no chemist likes to come back to a dirty glassware, and no one wants to use it after. Once this has all been washed with soap effectively, you may dry your glassware completely of water. Then it is ready to use for the next chemist. Thank you for exploring the chemistry of cooking eggs with me. I hope you enjoyed this video and learned something from it. I'd like to thank my parents for helping me film a little bit. I'd also like to thank Kayla for being such an awesome TA and bearing with me through this really embarrassing video.